Got it? I will begin with a word of prayer. Dearly Father, we thank you for this day, and I just thank you for this time we have to meet together and study your creation. I pray that you be with us, help us to glorify you, what we do, Lord, this day. In your name I pray. Amen. So this is lecture 5, which is on the Dihedral group and symmetries, not in that order. Bless you. The first part of this lecture, I need to tell you some rather general ideas. And one of those ideas is, what is a symmetry? So we'll get to that. Although, I suppose, to be honest, I'm not giving you the most general notion of what a symmetry is by any stretch of the imagination, but a pretty general definition. So, first of all, there's a very large group that I have been neglecting. Let S be any set. Then perm S forms a group with respect to composition of functions. And what is perm S? Here, perm S is equal to simply, F going from S to S such that F a bijection. So if you look at the set of all bijections on a set, that forms the so-called permutation group on that set. Now, as a specific example of this, perm of the natural numbers ranging from 1 to n is what we call the symmetric group on n symbols, right? So a symmetric group are a specific example of a permutation group, but this is a more general concept, all right? So we could also talk about permutations on Rn, and that's what I'll be talking about for the most part today. And what that would be is the set of functions from Rn to Rn which are bijections. This forms a group with respect to composition of functions. By the way, we know from Math 200, or should know from Math 200, that composition of functions is associative. So if part of a homework problem is showing functions composition is associative, you could just say, we know function composition is associative. We proved it in a prerequisite class. Or you could just say, we know function composition is associative. And that would be fine with me. So sorry if this comment's coming hours too late, but there's a comment for you. Now, you may or may not have actually proved that in your Math 200 class, but it can be proved for general composition of functions. So next up, definition, isometry. What's an isometry? If phi is going from Rn to Rn, has phi of p minus phi of q, the length of that, is equal to the length of p minus q, then phi is said to be an isometry. If that's true, of course, for all pq in Rn. How do we define length in Rn? What does this double bar mean? Just a reminder, double bar x is equal to the square root of x dot x, right? It's a dot product of the vector with itself. This is the square root of the sums of the squares of the components. Yeah? So the formula above can also be read as the distance from p to q is equal to the distance from phi of p to phi of q. It's a distance. It preserves, an isometry preserves the distance between points as measured by the usual Euclidean distance function. All right, that's what an isometry is. Okay. Theorem 2.54. Let phi from Rn to Rn be an isometry. All right. Then phi preserves dot products if and only if phi of 0 is equal to 0. In other words, the isometries of n-dimensional space with respect to the Euclidean norm, which preserve dot products, are precisely those which fix the origin. The origin fixing isometries are the ones which preserve the dot product. Preserves dot product. What that means, guys, is that phi of phi of p dot phi of q is equal to p dot q for all pq and Rn. That's what I mean by fixing the dot product. So let's look at the proof of that. Let's see, this is an if and only if, so let's do this way first. So assume, we call this thing star, assume star. We'd like to show that phi of 0 is equal to 0, right? Well, notice that phi of p dot phi of p is what? By assumption, p dot p, right? But what's p dot p? That's the length of p squared, right? The distance from the origin to the point p squared. But what about 0? Try p equal to 0. What does that give us? Phi of 0 dot phi of 0 is equal to 0 dot 0 as 0 vector, right? So that's the length of the 0 vector squared, which is 0. In other words, the length of phi of 0 squared is equal to 0. What's that say? If the length of a vector is 0, what vector is it? It's just the 0 vector, right? Because we're talking about Euclidean length. So it's, yeah. Now the other direction of this implication is a little bit more subtle. Let's try it out. Mostly an exercise in dot products and the algebra of dot products. And it's a little bit sneaky, so I'm going to be careful to follow my notes. So first of all, we notice that the length of p is equal to the length of p minus 0. But since it's an isometry we're working with, that's the length of phi of p minus phi of 0, right? But we just proved that phi of 0 is, well, excuse me, we're not proving it, we're assuming it, right? The other direction we should assume, I'm sorry, but bad instructor. I should say assume what? What's at the start of the reverse? We must make our assumption. Assume phi of 0 is 0, right? That's our starting point. Just like at the start of the forward direction of the biconditional, I said assume star, right? We must assume the starting point. Otherwise, it's a bad proof. All right, but we're assuming phi of 0 is 0, so this is just equal to the length of phi of p. So there you go. We've got the length of p is equal to the length of phi of p. Right. So consider the following bit of sneaky algebra. And here we go. The length of phi of p squared plus the length of phi of q squared minus twice the dot product of phi of p and phi of q is equal to bracket phi of p minus phi of q dot product with phi of p minus phi of q. The equality I just wrote down is just straight properties of dot product is the fact that the dot product is commutative and it distributes. You can easily work out that the right-hand side is the left-hand side, right? And then what? So that is nothing more than the length of the difference of phi of p and phi of q squared. But remember, before either of the purple or the red part of the proof, there was the black part of the proof, which as a precondition, the precondition we're assuming throughout this is that phi is an isometry, right? That's assumed from the start and for both parts. That's given at the start of this. Phi is an isometry. So phi is an isometry means that the length of phi of p minus phi of q is equal to the length of p minus q, because isometries preserve distance, so between points. So this is phi of p, this is p minus q squared. And then essentially by the same calculation, we can rewrite that as a dot product, which is p minus q dot p minus q. And what happens with that? Well, that gives us, length of p squared plus the length of q squared minus twice p dot q. And so what you got to do then is simply look at what we got. We have this is equal to this over here, and notice that that is actually equal to that, and notice that this guy, wiggle, 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 is actually equal to this guy, wiggle, wiggle, wiggle. And so therefore, thus, phi of p dot phi of q is equal to p dot q. Right, because we got a minus 2 on both of them. So there you go. We have proved that if the origin is fixed, likewise the dot product is fixed by an isometry. So, dot products are important. Why? Why are dot products important? So we have the Cauchy Schwarz inequality, right? So like v dot w, the magnitude of that is less than or equal to the length of v times the length of w. This is the so-called Cauchy Schwarz inequality. This is true in Rn. And the reason that that's important is that for v and w non-zero, we have that minus 1 is less than v dot w over the length of v times the length of w is less than or equal to 1. That follows from the Cauchy Schwarz inequality, just dividing both sides by the norm of the product and thinking about what absolute value means. So what this means is that that quantity in the middle is bounded between minus 1 and 1, which means it can be identified with a cosine. Or sine, but we use cosine. And so we say that this is equal to cosine of theta. And so by definition, this is cosine of theta, where theta is an element of, how's it go? 0 to pi. And this gives us a concrete analytic definition for the angle between two non-zero vectors. This is how we define the angle between two non-zero vectors in Rn. Here's v, here's w. This is the angle theta. And if you have some time on your hands, you can prove that this analytic definition that I just gave is in fact equivalent to the geometric definition of angle sweeping between two line segments by looking at the specific plane in which both of those line segments lie, and then going back to whatever primordial notion of angle that you had been introduced beforehand. But for me, that's the definition of angle with respect to the Euclidean way of thinking. So great. That's how we define angle. And that allows us to get yet another theorem. And there's a typo in my notes right now. If you don't mind, I'm going to erase this part of the proof. In fact, I'm going to erase the whole proof as it's beside the point now. In fact, I'm going to write the next theorem over here. theorem. Oh no, time flies when you're having fun. Let's see here. Theorem 2.55 says if phi is an isometry with, and this is what's missing, phi of 0 equals to 0, that's important, and theta is the angle between v and w, then theta is also the angle between phi of v and phi of w for vw not equal to 0. In other words, origin fixing isometries preserve angles between vectors. And the proof of that is pretty simple, given theorem 2.54. See, because we can look at cosine of theta, right? By definition, if theta is the angle, let's suppose that theta is this angle, right? The angle between v and w. So if theta is the angle between v and w, then by definition, cosine theta is what? It is v dot w over length of v, length of w. I am loving this marker. But if phi is an origin fixing isometry, then it follows that this is phi of v dot phi of w over length of phi of v, length of phi of w. Now I used a little bit sneaky step right there. How did I know that the denominator is also, how did I get that v was equal, how did I get that the length of v was equal to the length of phi of v? How do you know that? I should probably do that before I get to this step. Note, the length of phi of v is what? If we take the length squared, that's phi of v dot phi of v, right? Which for the origin fixing isometry is v dot v, which is the length of v squared. So side bubble, sorry, I should have done that before I got to this calculation right there, but you can forgive me. Or don't. It's up to you. I mean, I do have 5 children and a house to pay off, though. So be kind. I know, he's using his children. Oh, monster. All right. Let's see here. Now, so anyway, the point is that those quotients are the same, but the quotient on the right is exactly the quotient which defines the angle for the image vectors. So this would be the cosine of theta prime, where, you know, I'm calling this thing here theta prime, right? But the thing is, both theta and theta prime are taken between 0 and pi. So if you have the cosine of two angles between 0 and pi are equal, it forces the angles to be equal. Right? Think about that. Between 0 and pi, cosine is injective. It never hits the same value twice. So that means that implies that theta is equal to theta prime here, which is what I set out to prove. So, great. Origin fixing isometries preserve angles. Moving on here, where was I? Oh, yes. So you might not be surprised to find out that origin fixing isometries are important. And here is a definition. So we're going to say isom of Rn is just equal to the set of all isometries. In contrast, orth of Rn, this is going to be phi in isometries of Rn, such that phi of 0 is equal to 0. So the orthogonal group, as it's called, the orthogonal group is itself a set of isometries, the subset of isometries which fix the origin. So there's that. You can prove that this orthogonal group has 3 kinds of things in it, actually. My bad. you can prove that the isometries has three things in it. It has translations, rotations, and reflections. So this guy has translations, rotations, and also reflections. The translations are not in the orthogonal group because they don't fix the origin. Like a translation, those are easy. So if I had like phi of x is equal to, say, x plus the vector 1, 2, 3, n, giving an n-dimensional example. There you go. So if I take x plus a vector, that's a translation. It will preserve the distance between points in kind of a stupid way, right? If you take 2 points and you translate them, still the same distance between those 2 points, right? But the angle between the vectors is not preserved because over here the angle between the points and the origin would be like this. But if you move them over here, the angle between the points and the origin, it's like that. It's not the same angle. Angles are not preserved for translations between points and the origin. All right, I'm shut. Enough. Translations are isometries, but they're not in the orthogonal group. We can prove actually that the orthogonal group either has rotations or reflections geometrically, where rotations are what that mean. What you perhaps have an idea of what a rotation is already geometrically, and a reflection means that there's some line of reflection over which you're turning things over, right? All right, let's not try to do much more in Rn here. Just a little bit more. So, theorem, every isometry of Rn is a bijection. Oh, why is that interesting? What's the definition of isometry? It's just that it preserves distance, right? So that's perhaps a little bit surprising. Maybe you might think that there's some kind of weird nonlinear, not one-to-one thing that still preserves distance somehow. But no, it's impossible. So you can prove every isometry is a bijection. Translations are bijections. The inverse of a translation, for example, I would just subtract that vector. That would be the inverse. So every isometry is a bijection. Every isometry fixing 0 is in fact a non-singular linear transformation. This is a theorem you can prove. And so with that in hand, that means that this up here, the orth Rn, is actually a set of what? So this theorem says that one thing. It says that this is in fact a set of linear transformations. What does the first sentence tell us? It tells us, provided that in fact that these are groups, in fact you can prove that both of the things I've written up here are in fact groups. They satisfy the axioms of a group. And here's the deal. Just to summarize what's going on here, orth of Rn is a subgroup of the isometries of Rn, which is itself a subgroup of the permutations on Rn. Now, we're interested in the dihedral group. The dihedral group fits into this story further down the chain. Below this, you have subsets of, like we call it omega of S. This is the so-called symmetries. Symmetries of S. What is this symmetry group of S going to be? Here's what it is. Omega of S is by definition phi in the orthogonal group. So let S be a subset of Rn. Then the omega of S is phi in the orthogonal group such that phi of S is equal to S again. In other words, the symmetries of S, all right, which I'm calling omega of S, the symmetries of S are the set of orthogonal transformations which move S to S. They just keep S to itself. Now, each point in S doesn't have to be fixed, but as a set of points, they're fixed. All right, so the dihedral group is based on the case that this set S are like the vertices of a regular polygon. For example, I gotta be careful. Oh, before I move on to the dihedral, one last thing to say about this family of thinking. You can also talk about orthogonal matrices. So like orthogonal matrices, which are sometimes called like ONR. That would be the standard matrix of phi, such that phi is an orth of Rn. So the set of standard matrices of orthogonal transformations are the orthogonal matrices. And those make for great problems. They're actually, really nice matrix groups we can study. I have more to say about those some other time. Let's go on. All right. It's a straightforward exercise to prove that the set of isometries or the set of orthogonal transformations actually do form a group. You could use the one-step test or the two-step test if you like, and because they are subsets of the set of permutations, which we know is a group, right? In principle, you could use the subgroup test for problem 1 in your homework about affine functions, right? Because the affine functions are a subgroup of the permutations of R, right? Functions from R to R, bijective functions from R to R form a group called the permutations of the real numbers. The affine functions, your problem 11, it's problem 11, right? That would be in that world. So you could use the subgroup test there if you wanted. But if you've already just verified the axioms of a group, showed that that it is in fact a binary operation, it's got closure, you got identity, you got inverse, it's got associativity. If you've done all that, that is perfectly good and a healthy and responsible way to do problem 11. I'm happy you did it that way. So there you go. Definition. Let Dn denote the symmetry group of a regular n-sided regular unit length n polygon. And we will call this the dihedral group of order 2n. Notice that the 2n is in that sentence, but it's an n up there. That is not an accident. That is not a typo. That is my convention. That is our convention. That is your convention. There you go. So, all right. So this is interesting, I think. Now, I could make this definition without going through everything I just went through. The reason I went through what I went through is that I think it's important to understand how the dihedral groups fit into a much larger discussion of symmetries, which the meaning is, is tied to this concept of isometries with respect to the Euclidean distance and so forth. But how much of what I just did actually comes to bear as we work on examples of dihedral groups going forward in this course? Not that much, actually. But I think it's important to understand the origin of this group, and the origin of this group, I think, is largely geometric, right? So let's start with an explicit example. And what I'm going to try to do is use some color coding. So we're going to talk about triangle. We'll talk about D3. All right? And so what I'm going to do is I'm going to label the vertices 1, 2, 3 like that. to start with. And so the first thing I'm going to do is I'm going to rotate the triangle. Rotation by 120 degrees, right? Like so. And we'll call that R for rotation, right? And so that does what? Counterclockwise, counterclockwise, right? So that moves 1 over here. It moves that 3 upstairs. And it moves the 2 down here. Then rotate again, right? What happens next? Counterclockwise, right? So 1 goes upstairs, 2 goes over here, 3 goes over there. What happens when we rotate again by 120 degrees? So counterclockwise, 2 goes upstairs, then 1, then 3, right? Have I clockwise labeled and counterclockwise rotated? Let's fix this now. Let us fix this now. I'm sorry for wasting a minute of your life, but it's for our best to not do this. Trust me, no good comes of that. Oh, 1, 2, 3. Yes. 2. Wait a minute. Goodness gracious. I have problems, obviously. Let's see here. So 1, 2, 3. 1, 2, 3. All right, and then finally we're back where we started, right? My point is simply this. What have we shown geometrically? We've shown that the rotation by 120 degrees done 3 times in a row gets you what? Back where you started, right? So we can express this by saying r cubed is equal to, the identity, right? Well, let's use 1 for the identity here, if you don't mind. So r cubed is the identity. And then, so if you can imagine that this was a sheet of paper, right? Imagine it as a sheet of paper. Hopefully I may be violating someone's cross-country tennis convention. I will try to use the piece of paper without, all right, is there, I think we fixed it. All right, so the point is, if you think of this as being a piece of paper, we've rotated it, right? And then again, and then back where we started. But the point is, it was always this side of the paper, right? Every one of these rotations, the same side of the paper stays up. Now, the other thing we can do is look at a reflection. All right? And so reflection along the vertical line here. And so there 3 stays fixed, but the 1 and the 2 flippity-floppity. Right? And so that transformation we'll call F for flip. I don't know. Or just because it's F in my notes, how about that? And the point of that is, though, in order to achieve that motion, what do you have to do, that symmetry transformation? You have to take this triangle, and you have to, see, this is 1, this is 2, this is 3. So in order to do that, you have to flip it over to the other side of the paper, right? So this flipping motion, you can't actually achieve in the plane. You actually have to flip the triangle out of the plane to come back in. It requires a motion in 3 dimensions to achieve this. This is not a physical motion of flatlanders. Like if you were stuck in 2 dimensions, you could not achieve this reflection. But anyway, there it is. And then to get back to here, what do? Just the same thing again, right? So F squared is the identity. And I was thinking it would be good if you had a picture to think about the triangle having two different colors. Like maybe one color is blue, the other color is green. So like you flip it over, you can see it's green, right? This one's blue. Maybe I should use red, oh well. All right, I got blue one in my hands. Now what happens when we combine these? What if we do, let's see here, what do I want to do? Is there an error? How about if we try what would FR look like? Well, I'm sorry, let me say R. What would RF look like? So let's see here. This is R. And so what if I do RF? What would that be? From here, I have to do an F, right? So what's that get me to? We have a 2 upstairs. We flip the 1 and the 3 like that. Yeah? We flip the triangle over. Now we're looking at the green side again. Yeah? So this is RF, starting with our standard triangle. And what would that, let's compare that to F. We can compare that to FR squared. Where's my R squared? I want to do FR squared. So, stink. I want to calculate FR squared. I'm going to have to work it out. So we start with the triangle. 1, 2, 3. To do FR squared, I have to do R. I do R, right? Can we do R squared in one step? Would that be okay? I think we can do that. We rotate 2 times. What does that take me to? The 1 goes to here, then to here, right? Do you guys agree? That's R squared acting on triangle? And then flip it. Flip it. 3, 2, 1. Wait a minute. Oh. What have I done? I start with 1, 2, 3. I start with 1, 2, 3. I rotate once. I rotate once. Oh, I did it in the wrong. I see what the problem is. I didn't do RF here, did I? I did F. This is FR. This is FR because it's the same thing with the permutations, right? We have to do F first. So I should have done this F, and then I should have done R like this. This arrow is the wrong one to do. I should go first F, then R to get RF. So what happens there? One. The 3 rotated down here, and the 2 rotated over there, right? Again, we're on the green side of the triangle, just like we were here. And I think you can see that this and that are what? It's the same output, right? So I have shown geometrically that RF is equal to what? Equal to FR squared. By the way, that is FR inverse. I hope at this point I have convinced you that thinking of the dihedral group with pictures, I mean, I think it's important to go through this. I think it's important to be aware of the geometric origin of the dihedral group. But I think it's equally important to divorce yourself of this thinking as you actually work on problems in this semester, because there's a way better way to do it. And that is in terms of what are called generators and relations. All right? Or you could say it's a formal algebraic presentation. Now, in the notes here, I have three different ways actually we look at the dihedral group. The one is geometric, which I just spent the better part of 40 minutes trying to explain. The other is algebraic, which I'm about to explain. And the third way, which I probably shouldn't even spend class time on, is as a matrix. I actually give matrices in the notes which describe the dihedral group as a particular set of 2x2 matrices. And so you could build the dihedral group in terms of 2x2 matrices if you wanted to. But I really think that the generators and relations viewpoint is by far the one to be preferred. And that's the one I default to going forward in here. If I can find my notes, it'd be awesome. Come on, where'd you put them? Oh, it was me, wasn't it? Let's see here. I don't know. Come on, where are they? Oh, here they are. So, oh, come on. It's weird if you don't plug in the cable that no one can see it, you know. So in summary, what we have just learned geometrically is that the dihedral group D3, it's got the identity, it's got the rotation squared, right? It's got the reflection F, and then you can also have so-called rotor reflections, yeah. So you can have the reflection F, you have FR, you have FR squared, right? So these are the possible, symmetries of the equilateral triangle in the plane. Now, that's a group, in fact, that's a group with 6 elements. Do you care to guess what it's isomorphic to? What's that? S3 is correct, yes. And I have a proof of that in this section, actually. But here's how I would like for us to think about the dihedral group going forward. We'd like to think of it as the set containing the identity, a squared, all the way out to a to the n minus 1. These are the these are the rotations. And then all of these guys, b, ba, da-da-da, ban minus 1, these are the reflections. And by definition, we have that the order of A is n and the order of B is 2. And then this relation that BAB is equal to A inverse. That is logically equivalent to what I just derived. So we just had that, how did it go? What was it, F? I forgot already. Was it RF equals to FR squared? Can you guys tell me? All right, so if I want to solve that for, I can multiply both sides by F. I get FRF equal to F squared, R squared, but that is E times R squared, which, by the way, is R inverse. So, in fact, the thing we worked out geometrically just now is indeed FRF equals to R inverse, which in this notation would be BAB equals to A inverse. The dihedral group is not commutative. Got to be careful. AB is not generally equal to BA. In fact, so. But this is a good enough time as any for us to introduce just a new way of thinking about how we talk about groups. And this is an important viewpoint and a very nice and simple viewpoint for us going forward, which is the generators relations idea. And so here's how it works. To describe a group, you give a set of generators here, put a vertical bar, and then you list the relations which are imposed. This is generators relations notation. So for example, dn, instead of writing it like that with all that jibber jabber, you can just write a comma b, such that the order of A is n, the order of B is 2, and A and B are related like so. BAB is equal to A inverse. This is part of a larger discussion of something called free group and words. I'll just say a word about it. Pun intended. Haha. So here's some words. You can talk about the free group on the symbols AB. What that is all possible words in A and B and A inverse and B inverse. So here's some words. Ba 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 ba. And I don't know how to say that one, but there it is. But in fact, these are inverses because the way you multiply in the free group is just to concatenate words, right? So like if you had a conversation with a friend, you could multiply them by just like pasting them together, right? That's the operation. It'd be pretty cool if you had a conversation with a friend and they said something afterwards and then like you put them together and they just like canceled out. You know, it'd be interesting. But anyway, silly comments aside, there is something called a free group. You could talk about words, concatenation of words. This is a very well-developed subject, which I am not doing justice to. You should read the Wikipedia article if you're interested. Let's see here. So, so what I've just described is the algebraic, let's say, definition of Dn. To start with, I gave you a geometric definition of Dn. Geometric says that Dn is actually a set of isometries on the plane, specific linear transformations on 2 dimensions. This abstract algebraic definition with the A's and the B's is I don't know what they are. I mean, it's this free group, the generators relations, but it captures the essence of what it is. And the isomorphism between the two is very simple. Psi of A is R, psi of B is F. And this is part of a larger comment, which is if you want to prove 2 groups are isomorphic, if they're both written in terms of generators and relations, if you can find a mapping which sends generators to generators and maintains the relations defining the group, that also suffices to define an isomorphism. That's the final theorem that I wrote in this section. Now, this right here, I'll just tell you what this is. What this is I'm finding specific 2x2 matrices which serve as the reflections and the rotations that we're talking about. And after some work, you can prove that, I mean, rotation matrices are pretty easy to come by. That's cosine, sine, sine, cosine. And you choose theta as 2 pi over n. And that gives you an element of order n. But actually, I can build a group of 2x2 matrices, b to the k, a to the j, k equals 0, 1, j is 0 to 1 minus n. There is an explicit group of 2x2 matrices which has the same algebraic structure as this generated relations bit. Here it is explicitly. This is D4, which is a group of order 8. It contains, if you want to look at it as a matrix group, these 8 matrices. I don't know about you, but I would much rather work with E, A squared, A cubed, B, BA, BA squared, BA cubed, as opposed to 2x2 matrices and multiplying, right? Same algebra. So it's called dihedral because it's two-faced in the sense of it's not about just a triangle, it's about a triangle and its other side, right? So you could also talk about motions. Motions would be things that are actually possible in 2 dimensions. But all right, I digress. Here's an actual calculation, which is probably the most useful thing I've shown you today as it relates to homework you'll have to do. One of the things we should prove is, in fact, maybe I can do this, maybe we have time, I don't know. If I have if I have b a to the j, and I multiply that by b a to the j, what do we get? In other words, if I take any alleged, I called the last n things in the dihedral group reflections. So what I'm saying is that these elements behave just like B itself, or just like F itself. So my claim is that you can prove that this is actually equal to E. Let's see here. A crude and not quite, well, here's a engineer's proof of it, if you don't mind. So this is what? What would I have? ABA? Dang it. Or did I want BAB is A inverse? Oh, okay, so I need to put in a B and a B and then A, right? So that is A inverse. And I think you could insert copies of B, 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 B. Just insert a bunch of copies. I don't know. Let me not try to do it in 30 seconds. This you can prove. It can be shown that any BA to the J. This is what if you're going to work on when you're working on this. The first thing you should try to show. Prove this for arbitrary J. So anyway, here's a calculation. How to calculate? Oh, here it is for. I'm an idiot. I should just look at my notes. That's what I'm doing up here, right? A squared B is what? AAB, which is what? How did I get to ABA inverse? No, I'm not joking. I'm asking.
Because BA equals A inverse B.
Right, because I'm trading, exactly, I'm trading AB for BA inverse, exactly. Right, I'm changing this to that. Those are equal. And then, again, AB is BA inverse, so you got BA inverse A inverse, which is BA minus 2. So, and if you can do that, you can do it for 3 and so forth and so on. Anyway, tell you what, start a next class, I'll try to go through this. Anyway, let's go home. Or wherever you got to go. You could actually stay here. There's nothing happening in this room the next hour. Anyway, thanks guys.